Hi, welcome back to this video series on cryptography. In this segment, I will continue my discussion on quadratic residues. In particular, I will apply the concept of quadratic residues and discuss an identity-based encryption scheme. First of all, I will quickly recall what is a quadratic residue. Suppose you have a number A. We say A is a quadratic residue if we find another number R such that R square is equal to A mod n. We talked about this in my other segments. Please watch this. Please watch those videos. Okay. N is product of two primes P and Q, roughly the same size. Okay. We say A is a quadratic residue if we are able to find another number R such that R square is congruent to A mod n. R is also we can say both R and A are elements of the group Zn. This is the definition of quadratic residue. Okay. So what is the quadratic residuity problem? The quadratic residuity problem is, suppose we are given a number A. Is this number a quadratic residue number or not? Can this number be represented as power of 2 or not? With an additional constraint that, for example, let me use the Jacobi symbol notation. The additional constraint is so that if you take your number A and apply Jacobi symbol or Legendre symbol, because I'm talking about P being prime, if this is equal to, say, A Jacobi symbol with Q, okay, equal to, say, plus or minus 1, right? Now, if you compute A Jacobi, for example, with the composite number n, if you get the value plus 1, of course, because both of them have to be the same sign. Okay. If somebody gives you such an A and ask, is this a quadratic residue or not? You don't really know. We don't really know how to say yes or no. The question is A a quadratic residue? Okay. Can we find an R such that R square equal to A? Even if you don't find an R, you want to be able to say yes or no. Then we don't know how to answer the question. Okay, that's the quadratic residue problem. Many crypto systems are based on. I talked about it in Bloom-Shoop's crypto system, for example, and many systems are there based on that assumption. Now, let's get back to the identity-based encryption. So what is identity-based encryption? The idea of identity-based encryption requires a little bit of detailed discussion. Let me explain the idea using a diagram. So in traditional public key crypto system, the public keys are random numbers. In the case of identity-based crypto system, we use the identity of the recipient. Okay. For example, suppose Alice is here and Bob is here. Okay. Say Alice and Bob, or let's say Bob wants to send a message to Alice. Bob would need the public key of Alice in the past in traditional public key crypto system. In the case of identity-based crypto system, let's assume the identity is an email address for a moment. Okay, it need not be email address. It could be telephone number, or it could be domain name, whatnot. Okay, what if Bob uses alice.com? Let's use Alice's email as identity. Okay, A at email.com, alice.com. Okay, how do we let Bob use that identity to send an email to Alice? All Bob is going to do is he's going to apply a universal hash function h, takes the ID is the ID of the recipient. In this case, it will be Alice, right? Let's say ID of Alice is alice at example.com. Okay, let's assume for a moment that both Alice and Bob are working for example.com. Okay, just for a moment. This hash function is defined universally. Okay, anybody can call the hash function. That's an assumption, and I will talk about it a little bit more detail. There's some structure to the hash function as well. So this hash function becomes essentially the Alice's public. The output of the hash function becomes the Alice's public key. Okay. So in order to send a message, Bob will use the public key of Alice and then send a message. Okay. So let's say Bob wants to send an encryption of some data, some key, whatever. He will be doing encryption of his data using Alice. Alice A is small a is the Alice's public key and the data. Okay. Now, I'm just talking at a very, very high level. I will talk about the details in a moment. In order for Alice to decrypt the data, okay, Alice has to get a decryption key. So she need a private key that corresponds to her public key, which is small a. Okay, small a is her public key, which Alice, let's assume everybody knows everybody else's email address, and therefore they can call the hash function to derive a public key. But to decrypt, Alice would need a private key. So what will Alice do is, in the case of identity-based encryption system, there's a master. Okay, a trusted master is here, and the trusted master, Alice has to authenticate to the trusted master. Okay, how that authentication happens is outside the scope of identity-based crypto system. Okay, so Alice goes and authenticate with the master to prove that she is Alice. Okay, master will give back Alice a private key. Okay, so Alice will obtain a private key from the master. Okay, once the private key is exchanged once the master dispatches the private key, now Alice can decrypt the data that was encrypted, okay, using her public key. So that's basically it. So authenticate, right, on this direction, obtain a private key. Okay, so she gets a private key from the master. All right, that's pretty interesting because from Bob's perspective, he just calls a universal hash function using the ID of the recipient, in this case, alice@example.com. You can add more attributes. For example, you could say alice@example.com, and then you could say it must be valid only in the month of October. So you could put October as part of the ID. And so the message cannot be decrypted in November because the private key that she will receive from master is only valid for October. So automatically you can handle expiration and key rotation, okay, in this manner. Okay, so this is the basic version of the identity-based crypto system. There are many variants that I'm not going to talk all of them. Today I'm going to talk about one particular implementation of this idea. So this notion of identity-based crypto system was formulated by Adi Shamir, who is one of the inventors of RSA. He proposed this problem that it must be possible to have public key crypto system without the notion of certificates. However, his publication didn't talk about an algorithm. So it was like in 1984, he published that idea of identity-based crypto system. Until 2001, there were no concrete implementation of that idea. Okay, so in 2001, there were a couple of papers, and I'm going to talk about one of the papers to start with. All right, that's basic background of the identity-based crypto system. So now let's dive into the details of this, how this is going to work, what is exactly the hash function, what is exactly the master's duty, and so on. Let's talk about that. Okay, so I'm going to talk about the quadratic residue-based problem, right? The solution is the particular identity-based crypto system is based on that particular problem. Okay, so what the master is going to do, this is master, right? Master is going to publish his public key, okay, and the key, of course, keeps his private key secret. So master has a public key. Okay, in the paper that I'm referring, they used. Okay, this is master, just to get the syntax correct. This is master. Master has a public key. In the paper that I'm going to show to you, they use M for modulus public key, but I'm going to use N because I've been using N for all my other videos. So that's the only difference. Okay, so master has a public key N made of, to be even more consistent, I've been using small n. So let me try to use as much as possible consistency. P times Q, okay. P and Q are primes hidden to master. Only master knows those two primes. N is public. Okay, so N is public. He publishes the N to the world. Everybody knows the public N, which is random number, because it's made of two random numbers multiplied. It's a composite number. P and Q are prime numbers. They are private. Only master knows them. Okay, he never shares that P and Q with anyone else. Okay. So the P and the Q have additional structure. The reason for that will be clear later, but at this moment you can assume P is 3 mod 4 and Q is also 3 mod 4. Okay. So this is the mathematical structure of the primes P and Q. Master would generate this P and Q and he keeps them secret. He only publishes N. Okay. So let's talk about the other steps now. What is the hash function? How does the hash function look like? So the hash function is basically taking, well, ID is a string, right? You can imagine string getting converted into a number. For example, call SHA, for example, take a SHA function, SHA 256 or 512, whatever. You get a number, okay? But that number has to have some extra condition, okay? So what the condition should, the value A that you get out from your hash function should have an additional property, okay? If you plug in A and compute the Jacobi symbol, remember N is public, N is public. So this particular condition must be true. Jacobi symbol of A with the modulus N must be 1. So how do we make sure that happens? One thing we can do is we can let the master publish another number, a non-quadratic number, non-quadratic residue number, such that, let me call that number Z, okay, such that Z, Jacobi symbol of Z is -1, okay? So Z is non-quadratic. Therefore, if h of ID is a non-quadratic, all we have to do is multiply it by that Z. Let me be more precise. We need the property that Jacobi symbol of A mod with over N is 1. It need not be quadratic residue, but it has to satisfy this property. Okay. All right. So we got this idea. Let me show to you the encryption algorithm. So here is the encryption algorithm, but I will explain it in a moment on my whiteboard. Okay. So let's talk about the encryption algorithm now. The encryption algorithm in this case actually can only encrypt one bit at a time. Okay, the message space is either 1 or -1. Okay, you can imagine like a binary number system, but instead of 0 and 1, it's 1 and -1. So only one bit can be transferred from Bob to Alice. Okay, so how do we do this? Okay, and the message, let's assume X is the message Bob wants to send to Alice. He has to decide either it's 1 or -1. Okay, and this is what he's going to do. He's going to do something like S is equal to, he generates a random number T in such a way that T Jacobi symbol of N, right, is equal to X. Okay, all right. So this is what Bob doing. So Bob will be doing a random number generation T such that Jacobi symbol of T with N gives an X. Okay, X is either 1 or -1. So what is the encryption algorithm now? The encryption algorithm is basically T plus A by T. Okay, T is something that Bob generated based on the property that Jacobi symbol of T and T with the N is same as X. N is public, so it's something he knows how to do T, he knows A because he can apply the hash function, universal hash function. And he does this, he does compute D plus A by D in mod N. So he gets the reminder and then he sends the S to Alice. Okay, there's one more thing I need to spell out. There are two components in the encryption algorithm. So this, let's call this S1. There's another component called S2, which is very similar in that he generates, let me call this T1 for a moment. This is T1, T1, T1. He generates another number called T2, which also has the same property that T2 Jacobi symbol with N is X. So he will use T2 minus A by T2 mod N. He sends that to Alice. So Alice gets a pair of numbers now, S1 and S2. Okay. So Alice is now given S1, 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 S2. She has to recover T, okay, either T1 or T2, of course. And now she will only use either S1 or S2 based on an additional property, okay. So what Alice is going to do is she's going to authenticate to the master if she has not done it earlier. She's going to authenticate and obtain a private key. And that private key is basically, let me explain the structure of the private key. So remember, the public key is just a number A with the property that the Jacobi symbol is 1, okay? So what is the private key then? The private key is another number R, such that R square is either A or minus A, depending on whether the Jacobi symbol of A over B, A over P is equal to A over Q. Remember, master knows the prime factors P into Q. So he can generate the root. If this is 1, Alice receives R, and she can do R square equal to A check, right? Because she knows R and she knows her A. A is her public key. If R square is equal to A, she's going to use S1. So she will use S1 if R square is equal to A, okay? Otherwise, she will be using S2. So remember, she gets pair S1 and S2. So if this is true, she's going to use S1 and discard S2. Otherwise, she will be using S2. Let's stick to the first part, R square being A. So she gets an S1, she has to recover X from that, right? So let's assume S stands for S1 at the moment, okay? So how is the decryption algorithm going to work? She's going to take the S she received from Bob, R by T square, okay? Since anything power 2, if you take the Jacobi symbol, will become 1. Therefore, the Jacobi of this is same as T over N, which is exactly what Bob had sent. Okay, so that's basically it. This is how Alice can recover the message bit that was sent by Bob, either 1 or minus 1. Okay, so in the next segment, I will explain why it is difficult to break this. I'll explain breaking this is same as breaking the quadratic residue problem in the next segment. Okay, let me first quickly run the demo and then we can wrap it up. Okay, so I implemented this, right, as proof of concept. All right, let's get this thing quickly. So a few important things to note. Let's start with the main first. The master generates public and private key. I'm just using a small key size for the demo purpose. 512-bit key, you should be using 2048 and so on. Let me just do 512 for the proof of concept here, okay. P and Q are private keys. Master will keep them private. Nobody knows other than the master. And remember, I said about the fact that the public key must be hashed into a number that has a Jacobi symbol value 1. If you don't have it, you need to multiply it with a non-quadratic number so that your hash function output will be a number with the Jacobi symbol value 1. So that's the Z that is universal, publicly known. So that's what this Z is about. Okay, you're randomly generating a Jacobi which satisfies that property. Okay, that you will get a -1 for, when you compute the Jacobi of symbol Z. Okay, and now Bob wants to send an email to Alice, for example. All he's going to do is he's going to generate a public key. Bob is generating a public key. Generate public key, takes the Alice's ID, and takes the master public key and the Z, which is the Jacobi symbol that is used for the hash function that we talked about. So Bob gets Alice's public key. Now Bob wants to encrypt, say, -1. He calls the encrypt function. He sends the message, Alice's public key and the master public key. Of course, master's public key is also needed. And then he gets 2 pairs, like on the whiteboard I used S1, S2. It's basically, I can also call it S1, S2 here to be consistent. And okay, so you have S1, S2. Alice has to obtain a private key from the master. So She will submit her public key. She has to prove her authentication to master. That's something outside the scope of identity-based crypto system. And she will get back a private key after she proved her. So that's the R that I talked about on the whiteboard. R is the square root of A. Okay. So, and then once she got the private key, right, from the master, she can call the decryption process, and that will help her to decrypt and get the message back. That's all. So let's try this thing. See whether, yeah, see here, the assertion worked. Message is decrypted. Suppose I make a mistake. Yeah, it fails. So what you have seen today is a simple identity-based encryption system. There are some limitations to the system. The way I have shown is subject to so-called chosen ciphertext attack. There are some integrity things that you have to build in to avoid that. But at the core, this is it basically. The important stuff I have shown on the whiteboard are basically coded here, right? How is the encryption process? Encryption process requires the user's public key, the recipient's public key, and the master public key. And the recipient public key is derived based on her identity. That's the beauty in the system. And the rest are all the same as what I have shown on the whiteboard. And the decryption process is over here. Let me show you the decryption. Decryption requires user's private key, user's public key, and the master's public key. Okay, master's private key is never leaked, of course. And remember, I said there are two options. Either the square root of R is A or minus A, and that is something the decryption process will check and select one of the incoming ciphertexts. There are two ciphertexts coming from the sender for each bit. Okay, of course, it's a little bit inefficient because you're only sending one bit at a time, but this is one of the key ideas that I wanted to share with you regarding this particular paper. The paper is written back in 2001 by Clifford Cox, who also invented something like RSA equivalent in the UK back in 1970s. All right, that's basically it. Thank you very much.